Hello, sir. Hello.
Good
Sir, not audible, sir.
Hello. Can you hear me, sir? Yeah.
now I can.
Now hear me, sir.
Yeah. Okay. I can hear both your voice.
Yeah.
Okay, thank you, sir.
Good morning to and welcome to Dr. S. Jai Kumar, SITAMS Engineering College. This is an AICTE sponsored AICTE program, STTP 2. We are conducting on today session. Sessions 1 will start in the morning and session 2 will be in the afternoon. So I would like to invite Mr. Lakshminarayan K to give the brief profile of our today's session's speaker. So, sir is the eminent speaker from IIT Bombay. So, sir, Lakshminarayan sir, please take over to the Jai Kumar sir.
Okay, thank you, sir. So I am very happy and glad to invite and introduce Dr. Jai Kumar sir, IIT Bombay. So he experienced a CTO with over 25 years of experience in digital signal processing industry and excellent reputation for resolving problems in signal processing algorithms and driving overall operational implementation resources are both. So he known to the world as a Dr. JK, and he advisor to few companies and drives deployment ready solutions by using AI in IoT Edge and also in IoT nodes. He began his career working in Hall, Crane Infotech, Mistral Solutions. So JK has been one of the core team head in the design and development of products like the Karok missions. So one that enabled Toyota Corporation Japan to become number one in the world for networked Korako. Another major achievement of the past has been his contribution in the development of the solution satellite radio receiver, which we in the 1990s and till 2010 recognized by the brand name World Space. He has been instrumental in the design and development of IoT solutions in domain of healthcare, ATM monitoring and smart grid. So a person inspired by Dr. APJ Abdul Kalam, where APJ quote, if you want to shine like a sun, first burn like a sun. So you will find you will find Dr. JK working 24/7. So, prototyping, triggering solutions of quality to every challenge in the field of the electronics and communication engineering. So, presently busy with working on deep learning solutions softwares for IoT Edge. So, refer www.jqs.com for more information on deep learning enabled work. So, he has skills on audio signal processing, speech signal processing, image processing, MATLAB, LabVIEW, Scilab, TensorFlow, used ASM, C, C++, Java, and Python. So he used his all these technologies for modern Navi wireless data link design and development, satellite radio receiver design purpose, and FM digital radio design and development purpose. And his work experience from January 2015 to at present, member founding team. So Renanu Semiconductor LLP Bangalore, and 2016 to 17 member founder team Genius Plus Technology Private Limited Bangalore. January 2013 to March 2015 member of founding team Pytech Systems Private Limited Bangalore. 2012 to 13 consultant in SL Utilities Bangalore Karnataka. 2000 to 2012 member founding team in Media Technologies Bangalore. 2001 to 2002 research staff in KU Levan University Belgaum. 1996 to 2000 project member Mistral Solutions Private Limited Bangalore. 1995 to 96 DSP specialist CRAN Infotech Bangalore. 1994 to 9 project manager Indian Institute of Technology Mumbai Bombay. So 1987 to 1988 assistant aero engineer Hindustan Aeronautical Limited Bangalore Karnataka. So and his educational qualifications in 2002 he taken research fellowship. Then 1999 completed PhD in Indian IIT Bombay. In 1990 completed MTech in IIT Bombay. In 1987 completed BTech in Aeronautical Engineering Madras Institute of Technology. In 1983 he completed his Bachelor Science Mathematics Tanjavur Madras University. In 1980 he completed his school education in Tanjavur, Tamil Nadu. Then he has international experiences also. He managed a team in international level, Boston, Bangalore, Tokyo. So during 1997 to 2001, and handled customer meetings in Japan, Taiwan, Singapore, UK, and Germany from 2002 to 2012. So this is very brief history about Dr. Jaykumar sir. So because of with this introduction, I am very happy we come across Jaykumar sir. Now I am very happy to I am requesting Dr. Jaykumar sir to hand over the session and to enlighten our participants. Thanking you, sir. Thank you to all participants. Thank you.
Thank you so much, Doctor, for your interesting. Thanks. They're all. I said I'm audible for all of you, or I need to put
No,
bit more.
audible, sir.
Super. Thank you so much. Thank you so much. Very warm, welcome to all of you for today's sessions. It's a well-planned sessions. I wish everything will go well. To start with the day, it's my duty to thank the Srinivasa Institute of Technology and Management Studies. In fact, I've been passing through that one quite some time when you go to Tirupati, but today I was so lucky and privileged to, present that institute on behalf of them and, share whatever the little knowledge I have. And I'm really thankful to Dr. G. GP Pavan for his enduring challenges to arrange this for quite some time for successfully. I'll wish him more energy to do a lot more things than these sessions. And also I like to share my gratitude to the principal of that institute. Without them, nothing will move. Even though whatever ideas we have of staff members and professors and students, and the directions come from the principal. It's lovely that directors and principal having that vision to give the knowledge to faculties. Of course, that will be expected to percolate it to students as well. Here, Dr. P. Ramesh Kumar, I'm sure he'll be in the, there, or whenever he comes, we can say hi to him and thanks to him. And of course, I think it's a very powerful, power-packed team to support this. And before that, I would like to thank Nagaraj, Dr. Nagaraj, HOD of CSE department. He'll be more, demanding person in the campus because all the students want to learn computer science. I'm sure he'll be, sharing his time to all the, irrespective of the department, whether the mechanical or a civil or electrical or electronics. I think order of the day, computer science department has to give 1/3 of their time to other department as well. I wish, principal will do that. Then we have a power factor teams here. We'll just start with the start with coordination session, KL Lakshman Narayana, and then we have Mr. T. Vivekanandan and Mr. A. Naresh Kumar, Assistant Professor, CSE Department. And also, we would like to thank Dr. D. Jagadishan, Professor's IQAC coordinator. It's a very big team. It is I'm sure yesterday all of you had a good knowledge sharing sessions. Today I also promise I'll try my best to get along things what we have been trying to pass it on over to you. With these introductions, again, I'd like to thank all of you. All these efforts will be very useful. If you all of you put your effort and your time to enrich the knowledge what we are going to share today, such that it can be much better than what we learned. So, thanks for all of you taking out the time. Time like this, coming and investing your effort in learning certain things which you see that gateway to for a future decade, maybe decades, like what was been 2019, 98, 99 in Bangalore. It appears to be the similar thing happening now 2019 and 2020 in certain sector. And also AICTE, thanks to AICTE for giving this opportunity to the window of or the sponsorship, whatever, which they can help us to do that. The topic which all of you know, explainable artificial intelligence and machine learning for solving learning problem using Python and TensorFlow. So the knowledge always will be with us. When we share the knowledge, then we need to pass that knowledge from one professor to student and student to friends and so on. So the similar things happening in the machines also. Networks are trained one place, and then that trained network passed on to another machines to perform that work. It is exactly happening how we are knowledge sharing in the human beings, in the machines also happening. But it's interesting to see explainable artificial intelligence, because normally we call it in mathematical the term called proof or logical deductions, correct? So this is the way it's happening around. In that segment today, I would like to share one of the experiments which we have done. It is called J7 app, which is a way ahead for a tutor nursery students. That means how the students can learn 0 to 9 by writing the on the handwriting, like a slates they'll write in, like that they can write it on the mobile phone, and then keep learning how to write a one, how to write a two, without much help from parents or from teachers. For a time like pandemic like this, they're all in the online only. So this application is created and developed by using deep learning and deployed in the mobile phones also. That's what we are going to do that. And also the faculties or the staff members are in this session, whoever did, please do ask the questions, because we don't want to postpone the question at the end, whether you may forget or we may not be know the appropriate time the question comes up. So it will be good, now and then you clear it, even take 1 or 2 minutes late, delay, no problem, but we clear it and move ahead. Of course, a good introduction is given, saying that, about my the journey in this technological world. Of course, they do mention about a lot of organizations and a lot of institutions which went through the last 25 years, 25 plus years. The fascinating journey it was. It has been there. I think it's more and more learning now than the olden days. So the real world projects. So what happens is when we do have a kind of is it visible now? Is it the real world projects? Is the slide visible?
Visible, sir. Visible, sir. Visible, sir.
Very good. Yeah. It says the internet connection is unstable. So maybe what I do working.
Okay, sir.
The real world projects, we have been, there so many segments are coming now, and the predictions, computer visions, and natural language. So the computer vision has been working last 15, 20 years on image classifications, but things did not go well for quite some time. But now, this last 7, 8 years after 2011, things went well. So we give focus more on the classification problem via computer vision. Of course, DL took over it. That's a core area which will be hanging around, but we'll see how things are progressing for our application, for Twitter application. Sir, that video is available. See, we see it now. One student writing will be. Maybe that video will not come to you, but I'll share that one in the chat sessions. All of you can take a 1 minute time to click on the link, how the a student learns from the. Okay. The plan is a deep learning tutor for nursery class student, and how do we make that, and what are the ingredients that we have been putting into that, what are the, how to make this tutor, and what kind of languages we use, like a C, C++, CUDA, Python, TensorFlow, the things. Sir, I need one one request from you. The full screen is visible now, sir, or like how does it like?
It is actually a box, like blank screen, sir. It is, but your contents are visible. Now visible, sir. Now visible.
It's a problem when computation in a given image data. The data also visible now, sir?
It is visible this screen, sir.
Now will be visible, I think. The data also visible. Problem one, the computation in a given image data. That's what the statement I put up. Correct? Is it okay, sir?
Yeah, that's okay, sir. Problem one, okay. Computation in a given image data.
Good. Then I'll focus. I'll not change the screen. I'll keep the screen as it is. So, the designs always be bring out the logical problem and then trying to find the solutions. So the challenges now here is, instead of text data, images are given. Can we do computations by using image as input? That's a problem now. Let us go into the first one. All of you can see this. There are the two nice looking flowers are there. I do not know local languages. So, we call in Tamil, I know. Other languages, I'm sure all know what is a flower name. So there are dominantly two flowers are in that. But also it is very, clear that these two flowers are independent, distinguishable. They're not, mixed together. Given this as input, I suppose we want to compute how many flowers on this image, then there is algorithms can be used. Everyone can come out their own algorithms, OpenCV or TensorFlow, object detections, and so on and so forth. Quite number of solutions or people are worked out and working on it. Research is continuing that, correct? So the same problem was classically called Maxwell-Boltzmann statistics, where the two particles, there are distinguishables. Then only they'll go through the Maxwell-Boltzmann statistics. that as a origin of our things of 1850 onwards, most on the electronics and atomic physics side. But if you see, the same problem become little interesting. Now we have a left side, we have a two, the first one. The right side, if you see, there are so many flowers are there. Here once again we can attempt to count them, how many flowers are there in that. There is attempt can be made. Still there is a kind of numbers we can come out. As a human being, we'll lose the interest to count manually. But if there is an algorithm, there is a computing infrastructure that will relentlessly follow it up, compute as much as possible accurately. But there will be error. I'm sure there will be error, some epsilon percentage, non-zero error will be there in that any algorithm which we even today we talk about it. But the same problem become little more interesting. The left side we see Maxwell-Boltzmann statistics based two independent flowers. Right side if you see the things, that's the challenge, correct? And the flowers are mixed together and one overlap another, and there is no clear boundaries. They are not distinguishable at all, indistinguishable kind of thing. They were not separable from one another. How the computation going to happen now? Object identifications, basically. That is the places there are a lot of statistics come on. Both Einstein is statistics applicable. In fact, most of you, when you have a if a computer, you are in good place now. You can even look at that. These all things what I'm presenting it nicely put it. The website which you created and put it on that also, jks.com, you can see that. So here what happens is, can we solve these problems? This research problem, maybe most of the faculties can pick your PhDs, or you can guide your students who are not, have an interesting, talented student. You can train them to handle the right side problems, because this is a kind of problem in the top brains and universities, and people are working on it. So I'll put all the three in one page. We can have like a left side is a computable problems, as long as we have a good algorithm to find out the object. I'm only talking about the flower, not the leaves. So the second middle, a computable problem, but the complexity is increased tremendously. So we need a better algorithm to do that. So that's essentially kind of challenges. But the last most is computationally not trackable problem at all. So how do you bring that last rightmost section into computably trackable? That can be a research problems, and things can go around that, whether statistically may not be proven. Algebraic methods, there may be a statistical distributions required for that also, actually, to get that. Sir, audio is audible, sir, now? Is it audible? Sir? Pavan, sir? Hello?
Yes, sir. Yes, sir. Yes, sir.
Okay. Because now and then it says internet is unstable, so that's the reason I'm repeating, sorry.
Yeah, I am following, sir. I am following.
Okay, so now we, the first problem, but morning we took it as a kind of computing with images. So the leftmost we have a image in which we can compute how many flowers dominant. The middle, there is a challenging algorithm can come out with that. Maybe OpenCV image processing plus deep learning together can solve this problem middle, but with will be some error in it, and it will not be 100% error free thing middle. And the last is a challenging one. I know, at least I think there is no deterministic algorithms directly say how many flowers is there. This is going to come with some statistical methods, a priori knowledge, and then by knowing that, we had to find out what could be the number of flowers in that. That could be a route, but I do not know. Young minds now, younger generation flowers, students can find a different way onto that. So how the problem is computing and counting. This basically counting. It's not even a computer. I can say counting become trackable to non-trackable for a given different kind of images. So the extension that you can see this tree now. In the tree, imagine how many colorful leaves are there. If someone want to find out how many leaves are there in that. So again, it's a problem. Computability is essentially issues, correct? People might say, why do we worry about it now? But of course, present generation, we don't have any application of counting this leaf. Maybe soon time will come, how much photosynthesis happened, what is the volume of oxygen generated, so and so. Someone want to compute those things in the agri field, then we need a kind of a tools and mechanisms to count, come out the formulas out that. But today we don't have direct applications counting the number of applications in the tree, but soon might come out there. These are the research problems, opening up by using computability of given image. So, and we said step back a bit. Olden days, Maxwell-Boltzmann statistics is applicable to identical but distinguishable. There should be separate particle on any type of spin. The molecule of gas or particle, and this is the way they have been, created the mechanics and the whole the formulas and things come out when 1850 to 1890 kind of times. But that was challenged by his own juniors and like later stages. Both Einstein statistics applicable to identical but indistinguishable. So they can be overlap each other's, and still we can do certain amount of computing estimations. So there are hints are given in these directions, but it's going to be more towards statistical mechanics rather than real mechanics on that. Things can go on now. But the same problems appears in this also. The people who gone through the electronics course, the fundamental physics course, we know the transistors, the valency bond into conduction bond. So the electrons are then valency bond, but they move to conduction bond when the charge is flowing, when the current is flowing. So in that, there is a Fermi. The Fermi was, level. That's Fermi level is where the valency electrons will be there. We do not know when they go to valency to conduction bond. So again, the statistics comes here actually, like how Boltzmann, Maxwell-Boltzmann and Bose-Einstein. There is a third statistic called Fermi statistics. The Fermi statistics also uses the temperature as one of the variable to regulate, find out, compute, not theoretically like cost thing, but statistical mechanics. There are formulas are given to compute the how many electrons goes from valency bond to conduction bond. So these are the things our elders have been 100 years back worked out for a miniature nanoscale. But now the similar ideas, can we borrow them into the computing on the image world? That was a question which I was thinking, rather I'm thinking on it, maybe that catches up some of young brains to work on that. Of course, we have one quick questions on that. Since we've gone through the bit of odd mathematics and statistical mechanics and computing on images, there are three things we are connecting. One is mathematics, which is all of us know, I don't have any issues. Then the statistical mechanics, which we borrow a lot of learning from Bose-Einstein, plus Fermi, plus Maxwell's and Boltzmann. So all these three independent research directions mixing up, and then we are finding parallel between our computing problem to their problem what they had with the particles mechanics. So here we have a question: objects in image A is supporting Maxwell-Boltzmann statistics. Objects in image B supporting Bose-Einstein statistics. Now, object detection and counting detected object is computationally trackable problem in image A, image B, or in image A and image B, only in image A or not in image B, only in image B and not in image C. So you look at some time, maybe today evening or whenever there, you find out, how whether which is that computationally trackable, which is not computationally trackable. In case if you feel there is a objection, there is a kind of innovation, you are most welcome to message it. Dr. Pavan and team, our coordinate team is very happy to get you a kind of a recommendations on the enriching this answers to this problem, but you can look at this quick recap and what we discussed about last 5 minutes. So we'll go to the second questions on that. This is also very interesting. What is the necessary condition on a given image such that computationally trackable algorithm is used to count the number of objects in a given image? Suppose when some man is coming and say that I'll give you so many dollars, can you count this number of objects in these pictures? So if they say that, then we have to say before even taking up that work, we need to find out whether it passes a minimum requirement criteria. So do we have such a criteria now? Correct. So to that, what could be the answer? So I wanted your help to go through that answer. Given image need to have a Maxwell-Boltzmann statistic. Second, given image need to have a Bose-Einstein statistic. Or third, A and B. So what's happening here is, so these five things you can check out five, or if you have something else also you can add it to that. This is essentially to trying to recap again what we on knowledge basis is our elders had 100 years back on a this is not computing science, is called statistical mechanics and atomic physics and so on and so forth. Now what is happening in the computing world, we just borrowed them. Of course, the input is not a numbers, input is an image for us. That's a premise for these two questions, 1 and 2 for us to understand more. So with this conclusion of the problem 1, what we had was we asked for is computations in a given image data. So if someone gives it one image, can we do computing on it? Can we count it? That's the first one I asked. First locate the objects, then count them. After that, people want to do something else, then we can do add them, we then subtract them and then multiply them, divide them. These are algebra on it. But at least I have very primitively like a group theory. The basic thing is at least we need to count them, whether that is possible or not. That's the first problem. Under that, we gone through the many stages, which you had seen it. And also you've seen this tree problem once. Of course, this is a popular house of Kanwal-Ricci. The Intes entrepreneur. He was an early IITian who went to US. 1960s, I think, 70s, he had a CEO and another successful entrepreneur in the very early days. Today, entrepreneurship is very popular word everywhere, but those days when we were young, these are not very popular word. We had to hide and seek and, quit the job and then take a hard life in the, a hard path in the life. So Kanwal-Ricci, you can what they call Google it. One of the ideal figure for us, for me, and I like look at him as guy who had done well. That is his house in the US. And when we're discussing and just looking at him, how does this kind of things happening? So this is shared. It has come from. So we almost, I think we're done with the first problem. Until unless if some of you want to clarify some questions, then we'll go to the problem 2. Okay, in case if there is no questions arises, I think you can later on also you can message it in the boxes, or you can give it to our coordinating teams as well. They will take it up. So the problem 2 here is computation in a given image data with the Maxwell-Boltzmann statistics. Now we are narrowing down. We took a very general. Now we are going back to the narrow down. Okay, fine. Other computations are not in a general image, but in an image which has a Maxwell-Boltzmann statistics. It is an image which I told you for this kind of images. Can we do the computation of this kind of images? That's the second question. We are narrowing down. We are leaving the tough problem. We take easy problems. So the easy problem, here itself you see how things are becoming a little messy. And a computations in a given image data with a Maxwell-Boltzmann statistics, right? So now you see this one. It's the evening time, of course, and evening, night time. If you look at the sky, enough stars are there. how do we get able to count them? Of course, we can say one or two, three popular, I don't know how many of you astronomy freaks who watches the sky endlessly. Of course, when I was young, I used to be a kind of guy in Aslan, Bombay to astronomy group. We used to go to a place called Wangani, near to Mumbai, Karjat, and there. A night, a whole night, sit down and then watch the path and draw a curve, and then morning we'll come back and then see how they moved and so on and so forth. It was interesting, but now I'm not doing it, but it is still in memory. But later on, I looked at that problem see a different way. Imagine I have a snapshot of a sky here. And can I count that number of stars in the given pictures? So at the scale of course, 0 to where the yellow is a star, and then 0 is a complete blue. That is a kind of background, correct? In this, can we count it? So if you look at these problems, how do we are going to approach it? So I have a little different methods to approach that. I'll give the guidelines on it. Of course, I did go through this a little interestingly with the support from one of the websites, with the help from them. I'm sure you can enrich this solution much better than what I gone through that. So the left side we have the image with expect a lot of stars are there. I cannot say how many stars. I can say a lot of stars are there, right? So but that kind of a problem. So now we want to convert this problem into computationally trackable problem. That's the idea. Then to solve this problem, right? When the input is not good, then we do call in the signal processing we call pre-processing. Whether any audio signal or image signal or a speech, when the things are not good, we do pre-processing. That's called filterings. And there are so many ways of doing things. That is a very important for all the industries, professional industries, audio and video and so on and so forth. So here also the image we need, I thought it's a pre-filtering will help us to bring this problem into a computationally tractable problem where, each stars are independent, they are distinguishable, they follow the Maxwell-Boltzmann, statistics. So to do that, on the right side we applied the filters, and then we got the kind of interesting things there. So here what happens is who gone through the signal processing and imaging. So you can see that the background become a dark, everything else white. So there is yes or no kind of things. That's way anything close to 255 is white. Anything close to less than 200 become a dark. That's the way this class pre-processing done on it, white and black. So here now this also not interesting. So this also not helping us, correct? So what I thought is we can apply Laplacian filters called Laplacian Gaussian functions. It's a 2D filters. Of course, X is one directions, Y is another direction. Spatial filter, not one-dimensional filter, the two-dimensional filters, correct? In the two-dimensional filters, we have the Laplace and Gaussian both together put. Then we can do a bit of interesting on that. Assuming that you apply, of course, you can write a program and this C or C++ or Python, or you can write in Java. Even Python also quite easy, you can write it quite easily. That code also there, we can share it with that. When we do that, the next thing is, of course, I put the code here itself, so you don't need to go for somewhere else. I put the code itself, and then filters. We need to first design the filters by using the parameters. Assuming that the filter system here, then we are going to apply this on that. After applying, we have this kind of a little enhanced picture on it. So on the third picture, what we have is
where
application of
values are specified as well as the desired values are also specified. You know that pair is required because this is a supervised learning algorithm. This is a supervised learning algorithm. Okay, now this algorithm starts. It is called the error propagation algorithm.
Sir, someone is talking, I think.
What you call
Sir? Sandoz, I think someone is, sir. Sandoz is. Santosh Taide sir is talking, I
It's just
think.
useful for the convolution
Yeah,
neural network design.
I'm removing, sir.
Deep neural network.
Okay.
Okay, so very important.
So what is happening is now back to things here.
To be able to use it effectively, efficiently, you should know all the terminologies. Okay, so what it is written here, you require Z1D1, Z1D1, Z2D2, ZPDP. That means all these pairs. 1,000 patients are there. That means Z1, Z2, Z like this, Z1000, as well as D1, D2, D1000. These pairs are available in the training data. Okay. Now, what it is written? Eta is greater than 0. Next step. This algorithm we are discussing, error backpropagation algorithm, and this algorithm you can implement it. In the morning, we have discussed perceptron learning, delta learning, similarly with some mathematical model. Similarly, here you are observing some mathematical models. Eta value, eta is greater than 0. So this is a learning constant.
Sir, is it okay? Shall we continue?
Continue, sir. Continue, sir.
Okay, good. Okay,
continue,
good.
sir.
So now, thank you. So now here, if you see the middle of that, we got the wonderful two-dimensional filters. Of course, we given the name also, and that given the easy code, you can code it in MATLAB, or Skylab, or LabVIEW, or even in Python. This left side code. We assuming that we get the filter, then we can apply the convolutions. So when you do the convolutions on that image, then we are having a little more better clarity than what we had this kind of things now. So when it, now there is interesting things are happening, which is like in the middle picture what we had, so many flowers in the font, right? So that's a place we are brought almost rightmost problem into leftmost one. What I'm trying to say that the problem was more of this originally to start with. The problem was like this. Now we are pushing that problem into the middle one. Of course, it's extremely difficult to push the problem leftmost. The rightmost problem we are pushing into the middle one. That's what we are doing by using image processing techniques. So there is the problem appears to be many flowers in the form, which is like that. Now the many stars on the sky, how we are going to do that. So
excuse me, sir.
Then, yes.
Screen is not visible, sir.
Oh, I think that what that happened.
Sir, screen is visible. Visible.
Oh, okay. Now is it visible?
Yeah.
Okay, good.
Visible,
so
sir.
I'll stick on to that.
Yes, sir. Yes, sir.
Because that cross voice came, I went again, other one, so that was okay. Now we have just crossed that problem like a top left, like a sky, and then a smaller trick of changing the background colors and things. We got something little interesting. And the third problem, bottom left, we have a trackable problem. And then still more work on that each item, then we have a reasonably good problem to solve that one now. So if we do that, then we'll come to know how many a number of what you call the stars on that. We can compute it also. So rightmost, so imagine this is what the problem going to be when you zoom it in the zonal. So this is maybe some areas we may not be able to do that. That can be error. That's what I was telling. The middle problem is cannot be error free, but there will be errors. But 95% close to 9, that kind of percentage we could be able to solve the problem in good sense. So engineering sense, we can give reasonably good solutions for that, assuming that we have object detection for every circle. for this. So original problem was this top leftmost, then brought into here. What happened is this mode of filtering, image processing, unbounded decisions, all those things are happening. These tools are mostly, we can get it from OpenCV places. Here, as you know, there is no AI put as of now in this things. It's more of image processing. OpenCV, tricks finally played havoc, have played good for us. So with this note, then we can go with the files are given. You can, and the source code also given, start count Python file. You can click it when you have the times, because these slides will be uploaded, and when you have a time also in the home, you can check it, and the sample file also given, and then methods also go on to that. So, and also if you want, where I learned from is a place called skykittimage.org. There they have much more than what I had done there. They have a little more there, so you can look at that part also. Of course, I did Jupyter Lab one, but you can use whatever the things you want, but the source code is given, you can directly run for this problem too. So we quickly recap with understanding in the form of questions. So assuming that we have a question here is, Maxwell-Boltzmann statistics helpful to count the number of stars in the wind_sky.kip. So assuming that's a statement, if that's a statement is given, does the following, which is a good, because of the following properties. Each star is independent assumption is said, valid. This distance between the stars is too high. Maxwell-Boltzmann statistics converts the color sky into dark sky. Are dark objects in the bright background or bright objects in the dark background? Are item D and item E are on the compute stars? So you just look at that, maybe more than one might be, enable them to make that statement. Maxwell-Boltzmann statistics helpful for count the number of stars. So the next questions, of course, here I just leave it without much answer. Use that file wind_sky.kip image and compute the number of stars, which you can do it yourself and tell how many stars are 308 stars or 287 stars or 294 stars. That maybe if you have a master's students, you can give them an assignment and then get improving them and then go at that. So I'm not given the numbers here. You can do it when you have a time and do that for question number 4. I think now we are crossed two problems. One, the first problem, we said that images input, what kind of computing we can do, but we said only counting the object is a computations. The second problem, we said given the image problem, how we can convert the difficult problem is to reasonably good computable problem. That's what we said. And then we took an example of sky, number of stars in the sky, where we come out a reasonably good way to handle it, like so engineering way. These are the two things we done that. Of course, these are the dry, very abstract things you might think, but if we solve these kind of problems, then we can write a nice applications for tutoring the children learning and so on and so forth. Like so, that's the way I thought. Decompose a problem into many logical problem and have the solutions. By using this, then we can build a better things later on that. So with these foundations, we move on to a third interesting problems, computation a given image data from microbiology lab. This is an ongoing pandemic one. Who they really want to go and see the, someone's blood also now, someone's, samples. Everyone want to do it in a remotely and possibly like, non-touchable kind of thing. Of course, most of us know now today, the number of tests are going on amazingly high. In fact, governments, every country has their own strategy to new way of doing this one, biochemistry lab. So in this one, if you look at here, the application is going to be very interesting. See, this is a cell scribe. So we need to count the number of items. The star problem is only one, we had a star or non-star. But here what happens, there is a background, then there is a red blood cells, then there is a wastage also. When they create this sample, they do put some other material to clean it up, and so, but the cleaning, that's not all going to be cleaned, there will be some waste. So that should not come in the count also as a, it's counted, that also become error. So difficult. So human beings are essentially counting today. Every microbiology lab we go, or wherever a blood test places, morning take the sample, they'll evening they'll give the results. So much time they'll count endlessly. So imagine we solve that second problem, then we can enhance bit more and to solve this problem also. We can count them and say this many white blood cells and this many red blood cells. This is sample is not cleared. So many places we found this kind of unclaimed thing also. That kind of reports automatically is maybe some labs might be there in Japan and in America, but I don't know whether in our country we have that kind of labs. Maybe in AIMS or Apollo or JIPMED might have, but that may not be doctor's problem. This is more a problem of computing science problem plus image processing science people problem now. So we need to help those departments of medical people to handle this without the human beings interventions. When they collect the sample, the counting can be done, by using methods like computer visions, or still we are not counted deep learning and AI, so I'm not using it. So doing the foundations for that actually. So hospital is homocytometer to get cytometer to count the blood cells. This is what I got it from the history. Conventional method of placing the smear under the microscope and counting the cells manually lead to erroneous results. And the medical laboratory technicians are put under stress. Deep learning driven system will help attain precise results in less amount of time, maybe cheaper as well. Of course, many people lose the job, but that's okay. It's a life saving, so they can do other jobs. Unlike star count, the microbiology sample, multiple objects are present, like a WBC, RBC, cell strain. Now we need to have a objects, so we have to filter them, and we need to filter this. A WBC filter you put, then you put an RBC filter you put, then you put a strain filter. One input is one, apply the filter and get them different thing, then I'll go for a counting. So this will be interesting. Some master students or like a talented fourth years students can take it up and do that. Of course, we can help them to do other things. How we can do that. So the filtered design is important for every object like a WBC and RBC and cell strain. If we do that, then the problem will become a star problem, because star is only one, right? Imagine everything is your red blood cells, then counting become another easy thing, right? So the third problem, when the multiple objects on that image, then we are trying to filter them and get them independently and then count them after that. This is the third problem. Here we have a recap here, a good recap. Maxwell-Boltzmann statistics applicable in a picture microbiology sample given in the previous slide. So question is, detect items present in it or provided total count on each item in the same pictures. Obviously it's present, but what happens is it is not a one object, correct? So many items, many classifications are there. So we had to refine this Maxwell-Boltzmann statistics also reasonably well to suit the multiple objects and their statistical distributions and distribution in the given volume of that. So that's what I think, but I left it open. Yes, C and D. I thought you people can add a value on it and get more stronger hypothesis on question 6, because microbiology is very different and Boltzmann is different, statistics is different. How you are going to connect them and how things can happen to them. Of course, with these three problems, when I keeps telling about Boltzmann's statistics. So what was interesting for me was the computing and the neural computing, the neural memory storage. These two are playing major role, in the Boltzmann's way of doing things. That's what we thought. But I personally believe that the neural computing is not a Boltzmann machine. It's more of a Bose-Einstein. That's what I think. But presently the researchers across the world, they modeled the neural computing as a Boltzmann film. That means independently, like neurons are independent each other, they were connecting together. That's what the present model. But I think that's not reasonably true. What we are going through today, neural computing can be like a Bose-Einstein formula where things are superimposed each others and things are become much more complex than what Boltzmann went. But however, let's go step by step. Boltzmann way, which is every the green one here, which you see V1 to V4, they're all a kind of neurons, which we can see them, we can impinge something on them. But there are other neurons, we have H1, H2, H3, there are hidden neurons, we do not know what is happening with them. So, but however, as a neural network, they're all interconnected, everything is connected everywhere. So that now here is Boltzmann machine is each edge, connected to other all edges. But this is not a restricted Boltzmann machine. We'll see next one. It's difficult to solve this problem. This problem itself very difficult to solve. Then imagine how difficult it will be solve the Bose-Einstein's statistics base. So we dilute this problem Boltzmann machine into some little diluted. That's called restricted Boltzmann machine. That is. Yeah, before going there, this is a gentleman called a professor called Geoffrey Hinton. Of course, he's a living giant who works in Google, and also is a professor in Toronto University, Canadian university. And he was, asking how our relationship to computers has changed. Instead of programming them, we now show them and they figure it out. He's essentially driving to image-based computing, like visual computing. That's what is the dream. In that, of course, he's a founding father of converting this problem into Boltzmann machine problems. And his research students. Of course, before going there, I have an encouraging statement, because as researchers, I don't know how many of you, but most of us, when we are in young, energetic age in IIT Bombay, of course, we look at the TFR as our role model. So you know how tough the life for the research students, because turning down the our papers and not much infrastructures. We have every month on month we have a pressure built on. So that's the time I encountered this success consists of going from failure to failure without loss of enthusiasm. That's a day-to-day saying for us during PhD times. Of course, properly we want to do it honestly and good and think. Otherwise, this may not be true as such as, because we had our. So when you look at this, we'll go back to our problems. No motivational slide. This is a problem where this Boltzmann machine network is diluted and then remove the interconnect between V's and also interconnect between hiddens. So there is a V and H only connected. So in that way, what happened? The problem is become a restricted Boltzmann machine. Then mathematically we can write the energy level of this network, and then find out the parameters which is driven this energy to optimal level, correct? Energy can. So this is the way the problem is formulated, and that problems get solved by different methods and algorithms and so on and so forth. What is the problem here is V1, V2, V3, V4 become input that they percolated H1, H2, H3. Do you know how much they percolate? What they even if they percolate, what kind of reaction they going to give. That's the kind of things which normally going to happen for a hidden layer. So I model it this way little interestingly, like, of course, every neuron also we have a biases. So mathematical, I put a little easy and simple out here is, there is a process called learning process. Like as human being we learn, as a neural network also going through the learning process. The learning process has two things. One is provide the weight, start the weight W, and start with the initial condition B, and then for given the situation like a Bayesian rule, and then find out what could be the H. What is the probability of, probability distribution for H, not the probability of H. What is the probability distribution for H? H is our these hidden layers. And this is the forward problems because we supply energy to the V1, V2, V4, and then we wanted what the energy distribution will be H1, H2, H3. That was a question. That's a forward question, correct? Yellow. So then, assuming that that part is done, then what happened? That going to propagate some energy back also, right? So then what happens? Question comes another one. For a given H1, so we know the W, and H1. What could be the V1? It's a reverse question. If there H would have been that state, what could be the V1, V2, V3? So that V1, V2, 3 is not correct. What we expected, then we go back and then V0 become V1, then get H2, then V2. This is what kind of iteratively going for thousands and thousands of times. This is called training the network actually. So in a simple mathematical terms, on a slide you can solve it, use it. But this technical outside used to solve the restricted Boltzmann machines. Right? So the here issue is now whether to training the network, what for we are training? That's a question comes, correct? To perform certain operation on the image data. That is our idea, right? So when to do that, if you look at this statement, reconstruction is different from regressions or classifications. In that, it estimates the probability distribution of the original input instead of the associating the continuous discrete value to an input example. So what we are telling that the probability distribution of that V1, V2 only we are getting instead of associate continuous discrete value input, like yes or no, whether it is blue, red. We don't have that kind of inferences actually. The probability distribution of V1, V2, V3 only getting from this. That's what we call reconstruction actually. That's classification different from reconstructions, right? So in the classification problem, what this Alex Krzyzewski is a Polish student. I think he was a student of Geoffrey Hinton in Toronto University. In 2011, this gentleman has done interesting work. So this is known as he and his friend, both of them only worked, I think his friend picture also. They formed this network. It's the first time, they had a 2 GPU hardware in their lab. But there one more guy, his name is, I tell you, the guy name is Ilya Sutkeskar. Ilya Sutkeskar. And Ilya Sutkeskar and Alex joined together, they built this network. So it's a very different network. Even the neural network was quite sometime last 20 years, 1991 also I heard from them 90 times, but nothing materialized like this beautiful thing. 2011, I think ImageNet competition, these boys are built, AlexNet, 2012, I have put the numbers here. So they built this network. The network is very different than what kind of network which we talked about, neural network, right? So his professor was talking about this kind of network, and mostly Hinton was talking about this kind of network. Boltzmann machines, and in 1986 onwards, you can see these papers, foundation papers. But what these boys have done, these two of them, young students, they built this kind of network. In that, they put their professor's role in rightmost. There's 2 layers, that 2048, 2004, rightmost 3 layers. Only they put a neural network. The left side, they brought something very, very new, which is no one was doing that. No computer vision engineers, or no lab, Google, so many companies around the world, none of them were doing that. They had IBMs like Amazon, but these boys put this network, and then what they did, they pumped thousands of images from ImageNet, and then used this network for classifications. Of course, now people have Jazzy names for each one, like feature extraction, and TensorFlow. There's all kind of people build up stories around that for their own interests and kind of challenges. But this was the early things, but they're not named in the Jazzy name. Whatever they essentially want to do, the image to neuron. This is a kind of pre-processing they done. What attracted me from these boys is they done the pre-processing in the image, which like what we done in the pre-processing here, if you see, problem 3, you see, problem 3 done, no, yeah, no, pre-problem 3. See, problem 2, we done a pre-processing. The input was for us is this, right? Input is this one. We brought this input into this form. This form. We whatever the tricks and trades and knowledge we learn in image processing, things we filtering, two-dimensional filtering, everything we use and brought it that. That's the way this come to this part, right? But this voice, similarly, they use this kind of a knowledge base from image processing domains and then brought this one into the rightmost. The neural network is sitting in the rightmost 3 layers, but the left 1, 2, 3, 4, 5, 6. The 6 layers are nothing to do with the neural network, right? They're all like a very different way of bringing the image data into the nice network form. So of course, that's a become foundation for the TensorFlow to come. TensorFlow is a framework as a kind of a thousands of PhD every years all over the world is getting up from this network called AICTE now. Of course, more detail I'm sure yesterday they would have covered or someone might going to cover. Since I leave it a very short note, he brought the problem of image classification is a computationally trackable problem, reasonably, it's not error-free, of course there is the error, by using the network called AICTE. Okay, that's with that note, I'll leave it here. Of course, this might be interesting. Of course, a lot of faculties, we do, last 1 year faculty development program, we kept on moving around India. So there, what happens is once they learn certain things, where they're going to practice, where they're making their children going to practice, that's a problem today we're facing in this place now. Okay, we have one laptop, might be have some Windows or some Python. Most of us doesn't hold a Linux laptop also, and we don't have GPUs attached to that to do the computing and so on. So, but these boys use that called GTX 580 GPUs in their lab. Of course, the professors foreign universities, the lab means they'll have a good infrastructures actually. That infrastructure only drives their lab's growth and project proposals and funding and so on and so forth. So it will be good for the young faculty, staff members, professors now who are in the lab. Build up your own lab, smaller lab. In fact, only these two hardware built up that big things for the whole world. You see, today the company like NVIDIA and all got a real life because of this experiment by these two guys. And in fact, NVIDIA today calling the company as a AI company. Before that, it's a gaming hardware accelerated company, correct? I think this hardware, those boys are bought for gaming acceleration only for their lab. But Alex and Sukesker used for that this hardware to run their network, the proposed this network to perform the image classification problems. What it done. So with this, there are two things become popular. One is that the new era of convolutional neural network come into picture because of their extension, pre-processing things. They did not do post-processing. In the signal processing, I don't know many of you would have gone through this course, signals and systems, and so the pre-processing the signal is very, very important before we going inferencing. After inferencing, the things are hardwired. We cannot do any computing further on it, right? So the pre-processing is, of course, analog domain. You can do like LNA, low noise amplifiers, and filters and so on and so forth. But it is extremely costly and challenging people. Only few people can do that. Digitally, there are many people can do it by copying the code and so on and so forth. So the moral of the story is, you build a nice lab in your own place, however smaller, it's okay, because Toronto University just had a GTX 580. Imagine it's a very simple one today's thing, but that given the mind-boggling results to the world. If not for them, it's the whole world is enjoying their research. Of course, these are 3 people in one place. Alex Sutkeswar is the leftmost, Alex, and his prof. Hinted these 3 in the lab. Of course, they were all very happy because they got an ImageNet competition. They won the challenge 2012. This challenge actually by using this innovation in the algorithms and this hardware. That's all. With that, things came up. Of course, that set up the thing. I think one of them leading person in Tesla or OpenAI or whatever, and process, he's, doing amazing work with the Googles and so on. So they are become a top brain in the world today. So with that, where it was leading, Alex and Elias' work led to the following graph, because they were 2012. You see, they were there in this place. Like Alex and Elias' place was 16.4% error rate was around the classification problem. After that, around the topmost universities all over the world, I don't know, Indian IITs are took part out in this research. That's a kind of things going on. Here we do say that we do a lot of R&D and things, but I personally see that kind of enthusiasm is not there. See, we have so many IITs. Not even a single IIT would have come through contribute this kind of researches across a thing. Maybe some IIT might have done, I do not know, but we get to hear them in the global things. Here if we see then almost 2013 become 11%, 14 becomes 6%, and 16 become 3%. Now become see there is a breaking place there. You see, as a human being, we have a 5% error seems most, and as a visual inspection says that we human being tend to do 5% error in that. So, but the machines are now doing only 3%. It means much better than human. I'm sure most of you know aware how difficult to score 100 out of 100 or 19. If you ask me to score 90, I would ask, attending your lectures out of 40 lectures. Even if I attend 25 lectures, I can score 80. But if I want to score 95, I have to attend all of your lectures, right? If you ask me to attend 100%, then not only I have to attend all your lectures, I have to work extra hours, 4 or 5 times of than your work, then only I can get the 100, right? So, but 100 is still not reached here. We are somewhere 97, I think. So, of course, people are going much aggressively now. This also is old result, 16. Now it's 9. We are in 24 years of things. The result data is not with me. So maybe some of you can check out what is the 3.1 become what number it is now. So what happens is now image classification problem later industry like everywhere become attendance now. The COVID things, Bangalore, most of the companies are taking attendance, not the fingerprint, not the face. Right. As soon as we go and walk in the company, in fact, Mistral where I do work for it, the camera just stands up and say, "Welcome, Dr. Jaykumar." So it just go in. That's it. So simple and easy. So because image classification problem. Before that, there will be a fingerprint. You had to go and put it. Then if you're not working, we had once again clean our finger and put so and so forth. Now those things are gone up. So it's become a routine work for millions of images classified across the globe for the different purposes. So within 7 years, 2012 was that innovation. Within 8 years, that become a popular application in the world today. Computing with images. And that too only the classifications, the bottom, not in other things. But still, we are not gone into that kind of foolproof thing, deductions, tracking, and also segmentations, semantic and instant segmentation. Still a lot of research going on other 4 items, but otherwise classification problems more to industry thing. With this one slide, bring out all the things what I discuss about Alex things. The consequence of Alex and Elias and Hinton's work, Professor Hinton's work, he brought out this kind of amazing thing within 4 years in the world. One research, late 2011 had a 26% error in the machine learning thing, but at 2016 that became a 3% error, which is in the essentially renamed called deep learning, convolutional neural network, and so on. So names become a very nice now, Jossy name. But what they had was this simple network, which this is a network. This is what happened. Of course, many of you now you have attended many lectures, or you also might have learned things. These are the network is people are associating with feature extraction, automatic feature map extraction. So many after things happen. Many people keep the naming. So after child bonds, people keep a different name for the child. So similarly, everyone keeping their own name, whatever they like for the network. Because, So that's the thing. I think we are done with that part of things. So which is come to on the theoretical side looks like y equal to h of u. So the h is a nonlinear network. U is input, y is output. What happens is the nonlinear network. To handle this nonlinear network, we need to kind of algebra in it. Like what are the algebra we need? We need to add them, subtract them, multiply them, and then divide them. So many places we cannot have this all four luxuries. Like an image, what I just keep repeating problem 1, 2, 3, we can only count them. Like like a group. It's like a group. Like how many members are in the group. That's all we can say. We cannot divide one image by another image. There is nothing existing, right? So if you give me a 4 centimeter scale, another rod 2 centimeters, I keep using that to scale and then divide the 1 and 0 two parts, like no 0. Like that we can do computing that. But there is that kind of algebra setup in this image set of all images. Only we can count how many of them are there in that. So if you see the mathematics required is very interesting. Out of that, the whole thing called rings, right? And the groups. In the groups, some of them have a two. One is multiplicative, another is group, another one called addition. Both the things defined we call rings, right? Little complex than group. And then we have when the groups is rings become outermost. Then if you still put some condition on that, we can say commutative, like A into B equal to B into A, say we a commutative one, right? Also order of multiplication doesn't matter, gives the same result. So if all of them and if you have two matrices A and B, that is not equal to B into A, right? So there are many of them, umpteen number of them doesn't follow into commutative rings, for instance. And then comes the integral domain. So domain is like A is equal to 0, that means A is 0 or X equal to 0. That's either one of them must be 0 in that domain. So 0 divisor, there should be 0 divisor there. So you might say that where it is happening, there are two tensors are A and B equal to 0. Need not be B is 0, need not A is 0, right? But still they they map into 0 domain. So integral domains is another beautiful things where we are guaranteed that any one of them, both of them 0 or any one of them has to be 0. Two non-zero things will not be lead to 0. That's what it means that, right? And of course, unique factorization is a little more, so given number 6, how many times we can factorize that 2 into 3 or 3 into 2, right? But we can factorize differently also. If some interested people, we can talk separately, like a 1 into minus square root of 5i. We multiply the 1 plus square root of minus 1 squared minus, square of plus 5 squared will become 6, right? So that way, the unique factorization domain is much more interesting on that. And that has become a principal ideal domain. PID is little more constraints on that. After that, put the constraints or Euclidean domain. Suppose we have a number 7 divided by 2, then we have 2 into 3 plus 1, correct? That's equal to 7. There are 3 times 2 sitting inside 7. With extra 1 is left out there. That's the place Euclidean division algorithm come. When that just may not be many groups may not be even able to define the Euclidean division at all actually. If we have that one, we are lucky, then we have Euclidean domain. In that, we have one more, like every element A and B equal to 1, that means B is inverse of A or A is inverse of B. Then that call inverse also elements are exist, that operation is there, then called field. That's a real number, right? So the computation is a big world. In the groups, what we attempted only to count them. We are not attempting any of them in this picture. So don't be misleading that, we are doing something amazing. We are telling very, very primitive, which nothing related this kind of complex algebra. If we had to do a good algebra, we need all these things to do that. We are not in that position. With this, we will take up recap in the form of questions. Number 7. Error in the image classification in deep learning based method is less compared to the human being or compared to machine learning method. This happens because, why this is happening? Let's think, right? Now maybe you can think on it. This is happening because DL methods are using convolutional neural network, or DL methods are using neural network, or DL methods are using CPU, GPU for training, or DL method does not require feature vectors, are real methods using too many kernel filters to learn future vectors. Correct? So I think in this one it's not a complicated, but it sees all the complex things in this problem. Maybe B except B, all other things are appears to be passing through that. But however, leave it to your mind to look at this one with more care. So I think with this, I know kind of things which we done last 20 plus minutes, we move on. If you have any questions, I'll have to take it now quickly, or we can move to the stage in which little more complex things further, like in particular, how would you deploy intelligence into the edge? That's the way which you go on it. Okay, since no questions, I'll just I want to take you a little glimpse of that one, little lighter note. What is the edge? Because people did talk about IoT edge, IoT node, cloud, that collabs and Azure, AWS, all the things are quite see things are happening and things are happening. But the real world problems are very different. Let's just see, look at the problem, how what kind of problems are prevailing around us. Because it's true in the whole world also. It's not only true for where we live in southern India, part of India, but the whole world. See, look at that smart home. People talked about smart city, but that word is nowhere hearing now. We don't know what happened to that word. But however, the concept of smart home have been very interesting from historically. People do live, people do communicate, people do, I think, but now people do compute also in the homes, correct? So the smart home is a place we need a kind of computing, because even the boy or a girl from any village also they need to go online. I'm sure most of your students are taking that lectures from this kind of places, because rich people may not come for studying, only poor people come for study, correct? That's assuming that hypothesis. Most of the people they take your online lectures from this kind of places only. And then what kind of infrastructure we have, what kind of edges we have, things happening. The smart transport, imagine this is a kind of road in which how the smart transport going to happen. See, smart healthcare, this way the work is happening inside that, what kind of smartness we can deploy. Factory, you can see amazing. This in fact real factory much more complex than this. A smart grid, that near to our home, if you see the pole, how many wires comes out of the one, the pole, you can see three number of wires, even the counting itself, another problem might be there. So how do you make that as a smart? And then agriculture, of course, I born from agri family, because I did lots of farming with support my father and mother when young. It's a place I contributed this society even before I went through my bachelor's in Madras Institute of Technology. And as long as I was in Tanjore, I was doing that. And agriculture is an amazing place. Not we don't use much of technology. Then I'm sure even now in our place in Tanjore, I don't think we use any of the technologies which people talked about it exactly. Then smart airport, of course, this is a place people, because rich people travel, there might be some smartness, elevators. I heard that Hyderabad airport is having smart trolleys, IoT trolleys, and so on and so forth. Like it's happening something in the airport, like automatic check-in, and people do that millimeter wave radar to scan our things. A lot of things are happening around that places. But all others are open, vacant. Lot more brains innovation can happen there. But why I brought it this is, and these are the places people do a lot of computing and things. If we go and ask, one village person, to my own friends there, when we were how much time will take to water the whole plant. We don't go for 3.47 hours or something. We do computing. Of course, we'll say, okay, this will happen, before, sunset, or before this, or before, we do have some quantification. The quantification is not the numerical number, but the quantification emerging out of a kind of computing on our brain by using images. what kind of pictures. When we are going to harvest, that's also computing, correct? We don't take that, maize. Suppose we want to harvest the maize, we don't take a maize to the TW, where is the, TW is one of the popular qualification lab in the Europe, right? We don't ask them put the maize in it. They will tell, okay, you can't, cut this maize and so on. We just go and look at that one and look at the picture of that, and then, discuss with, parents or uncles and say this what, okay, fine, it's a good time to harvest, I'll wait for 2 days or wait for 2 3, no, even, rain might come. So that the logic and the kind of deductions is not like a, kind of illogical thing. People do logical, very logical, and very pragmatic as well. The computation going their human mind, but that kind of computing doesn't happen in our world today. It's hard fixed numbers. 3 has to be there, 2 is there. Instead of 2, if you put 1, also it's an input error, right? Imagine you are booking the ticket. So your credit card number, last number you typed wrong, 1 number. Well, then do you think that our transaction will go through? Gone. But that is not valid for this kind of places computing. We cannot do that kind of computing when our inputs are ill-posed. Inputs are ill-posed. Images, one of them are ill, it's not a good trained one. We have to do a lot of pre-processing the input, then we can go to compute world. In the real computing world, the real computing science as 20-25 years before, the input is completely processed. The A has to be one number, B has to be another number. Then we can do add to them and see whether A is greater than B or B greater than A. This kind of things only this computing well done. But A and B are not properly given, then we have to pre-process it. In fact, now you see on the Google searches also, before you type, they pre-process your search type and then complete the sentences. A lot more new things are happening. Maybe now we need to inculcate the computing paradigm also different, rather than expecting for well-defined input as such. That's what I'm trying to emphasize here. That's what I'm trying to say, that when Maxwell Boltzmann is well-defined one. But both Einstein one is not well-defined one, right? There are superimposed, but still we have a computing on that one. So that's what the idea here is. So we need to have different languages, different transistors to do that. Maybe the last slide I showed what kind of transistor for to do that also actually. So what happens is, in the IoT world, the intelligence is almost there in the server side, which is the third one. And the smartphone kind of, that smartphone intelligence mostly for payments. Actually, I don't think anything else happening around that. Payments are watching, some YouTube videos and so on. So that's what a kind of intelligence in the smartphone also. But our network, whether a kind of 2G or 3G, 4G, there is no AI in it. There is no, of course, apart from delayed payment, suppose one day we got delayed payment, and then the voice message will come, keep harassing, facing that tomorrow you have to pay, everything related pay. But suppose say 10 times the call is cut, there is no information about that. There is a call drop, there is no information. So network doesn't bother about the service of it, but networks only bothers about the payment dates and dues only, right? So not much of intelligence are dropped in the middle of that one, but leftmost we can see and the edges and KD absolute zero intelligence, right? Absolutely, not gone into anything. Suppose a car is going on the road, the car is its driver only 2 things. Whatever the intelligent driver has, then car has, that's it. Car doesn't have extra intelligence than the driver. So suppose they are also not connected to that, but if we see Ola, Uber and all, now they connected back to the server. Some of the intelligence from server to car goes in the form of navigation, the next pickup and so on. So the knowledge also getting percolated from left to right, right to left in the form of like Ola, Uber services also today, like a Swiggy and thing. That's a lot happening in the IoT edges. So there, again, I was coming into how the computing world with the image is going to happen. So we'll take it. So this might be very abstract. I should skip it. This is more of like, how do you convert a given physical problem into computationally trackable problem in terms of sensors? Anything observer means sensor, right? So no one going to tell us this is what it is, correct? Suppose at microbiology lab which it took, that's observer. We are observing phenomena blood, and that we taken the picture of it, that become our input for us. Now we need to process some a lot more, things. So that may not be done within once. Until we finish the whole thing, we'll do the loop. It's called feedback loop, right? Then we do control all them. Say our blood has some more white blood control cells less, then the doctor recommend go something, some medications, and so control will go until the output is very good. Doctor will be keep doing this, right? So that is happening in every field. Even the student, when he writing, want to learn 0, 1, 2, 3 writing on slate, if he writes a 3 properly, the school teacher say, okay, fine, now write 4. If he's not or she's not writing 3, then kept on asking the person, repeat until they finishes write 3 properly. Assuming that time teacher is not there, only IBM Watson is watching the student. So the student say Kupuswami, so young boy, 3-year-old or 4-year-old trying to write a thing, and then he doesn't have parents are going to feel, and of course he cannot go to school because nearby there is not much school for him. Also he has to go 3-4 kilometers. So there is LKG, pre-KG for villages. Most of us we live that way. So for them, how do we are going to help them? Imagine they have a kind of computing, smaller like calculator kind of something, watching him, Kupuswami to write 1, 2, 3, 4. That time until he writes 3 very nicely, he kept on asking, no, not correct, good, okay, fine. So that's the way that application what we today we wrote is targeted, it's working properly nicely. That's the way the machine is coming in the loop. The machine become observer. The machine become observer, and the machine also expected to have the domain knowledge to then go and give the corrections. Otherwise, machine like a camera only, right? What camera will do? Camera doesn't do anything, right? Stores and that's it. So the place, because the intelligent doping more in the observer rather than the controller, and the interesting things are happening there. And I'm sure most of you will be look at this problem in future, research directions. But I'll leave it with the short note here is again, the intelligence getting doped in the observer to analyze a physical phenomena. Of course, that intelligence percolated for different purposes. So deploying, now the idea here is how to deploy such intelligence. Then what happened is, again, the request here is, suppose you buy a Samsung phone, someone buy a MediaTek, someone buys, some other company, Xiaomi, or so on and so forth. But what happens is, every company has their own Wi-Fi things, right? Rather Bluetooth or Wi-Fi. But one phone, Wi-Fi network will definitely connect to another phone. That's because the IEEE has 802.11. It's a standard. When the chipset comes out, they had to have the protocol, they had to have a message passing, they need to have adherence, the bitwise, what it means like, right? So that's called standard. Without that standard, it would have been extremely difficult. Imagine in the car of Maruti Suzuki tires putting it, Tata Sumo. No way, correct? So because there is no standard, everyone has their own way of doing things, correct? But we have to buy only the tires which goes for a Maruti and that way 800 Alto or whatever it is. But in the when you have IEEE standard, things are become multi vendors can come in. The competition, real competition will be appreciated there. There is no bias from one person to another. Whoever could doing that work they can do. But in intelligent deployments today, for here, this observer, there is no IEEE standard. IEEE also doesn't know how to do the deployment. Is there, suppose someone from Coimbatore deployed, someone from Ludhiana deployment, someone from Calcutta deployed. 3 boys are doing it 3 different ways, right? Or someone from Bangalore, they might be 4th way. So there is no unique way of deploying that one. That is why I'm telling is that we all know the kind of network here which is there. It's nothing, IEEE standard about this network actually. It's a built it. So everyone building their own Wimson's fancy, but one doesn't know this kind of network can be deployed in the given system places. That's what the challenge now. IEEE even today not work up. Of course, I keep asking IEEE to work up quickly and then come out kind of nice standard for that. Hopefully soon they'll come up. Maybe they may be looking for a sponsors like a nice college. Maybe colleges like what we are talking about, around 10, 15 colleges can join together and then create the standard, of course. Then once we do that one, IEEE can, review it and then, standardize for whole things. So things can go from us also. So a developed model works in the test data, then move the training to inference. So three things are happening, right? So without any standard, it is maybe within the lab to lab might be different. Forget about the city to city. So a lot more challenges and opportunities are coming in that. I'll leave the note here. You can, when you have a free Saturday, Sundays, or sometime in the lab, you have little times, you can go through this egg magnifies open source challenges. What happens is like of the massive success of Android, people are talking about open sources for IoT edges also, IoT edges and nodes. A lot more things are happening, and the things are, happening because of that's the way. Then on the top of it, standards can come, correct? Like in this. But what sad thing is, when you talk about today, that kind of environment which is thrown at our disposal of your students, undergraduate students or master or young faculty. Of course, in most faculties, we may not be keen on because we are supposed to do that. In the condition today, what happened is leftmost physics kind of, so many languages, so many frameworks, so many tools. When they know which is good, what is good, of course, everyone will come and tell what they know is very good, extremely good. They only use this one, don't even touch that other one. But if you buy a camera from one company, whether we can put our algorithms or our friend's algorithms, those things are not known. Oh, you written in OpenCV, no, we cannot run that. Oh, you put in a TensorFlow, no, your Python 2.8, no, it's not run. We need a 3.7. And confusions after confusions going on. There is no standard in this place. So, what is the result of that one? Is we had to get a nice standard for that. That's what I pre-emphasize this. Apart from there is no comment on the part of it. We have become very complex. The complexity distributor and developer and customers. So as long as developers understand the customer difficulties, so they'll adhere to tools and workflow what is there, because developers are more knowledgeable than customers, right? During the applications. But using the application, the user might be more knowledgeable than developer. They want to use it the way they like. So at that time they may not be go through all this just install this, you install that, and kind of things may not go through that. Like how Android phone, no one willing to do something, but still things are going well. So in this framework, we got something interesting for you to preview it, like a data set for training. That's the total and mouse together. Of the model, the data set and the model together, we have so many training platforms, right? Windows, Ubuntu, and then the cloud, and of course, so GPUs. So you can have a mini lab, any one of them into that. After assuming that done, the rightmost thing is deployment in the edges. That is the core focus for us today. What kind of edges we have? It can be Windows Edge or Ubuntu, or like it can be like an Jetson Nano, which is afternoon today I'll cover exclusively on Jetson Nano, how to deploy them into that. So edges are become very costly, and also big computing infrastructures coming on that. So that we today evening we can see the DL train. How do you train them in the server side, and how do you deploy them into the Jetson Nano? That's today evening we can see it. That step by step we can go through that. So that whole thing, put it in this kind of a data. It can be your data. That's what I was telling. Essentially, which is maybe I can recap that before going this. I mean, your data means no one going to come as a data. Suppose I want to help my my friends in a village, my village, or tomato farming. So then I know I have to work with him. What kind of images he has to collect from the farm field, and then how the thing whole happening. Like the things are not ready. So that's. Because since you're in early stage, maybe after 10 years things will be, or 15 years or 20 years things. But today we have to get our data. That's why get your data from the application which you like. that so here is you no need to worry about moving data to one place to another. That's a problem, correct? Got 2 terabytes of data. Imagine uploading the 2 terabytes of data and cloud is gone, time is gone. So I don't recommend that the top side of jumping from suicidal route. Then instead of that, it just keeps your data on your table. So that's why it means your own edge there. And then after that, you train that on your table. After training that, I mean table means your own lab. It can be a college, like how this guy Alex and Sutkoski done. They did not move the data to Google, Amazon. Amazon was there, by the way, that in 2012. It's not that Amazon. Those boys had done it beautifully in their own lab. Very nicely. Excellent way they architecture the whole the thing. Not only modeling, and even the training and the whole thing with minimal infrastructures. That too GPU G670, right? So we can have our own lab and that use our data to train it. After that, we can build our applications on that. Then after the building that application, we can deploy it on the edges. This can be deployed on other places. It can be you can put it open for the people, or you can sell it as for a thing. So this is where ecosystem can happen. That's what happening around now in this segment. So we quickly recap this as a question number 8 here. Deployment of TensorFlow model or Python-based model in IoT is required to optimize and quantize trained neural network model. This happens because, so I did not say much of it in the lectures, but the only complex it will, I'm not asking you all to think on numerical values like 2 plus 3 equal to 5, but adding 2 and 3 what is required. We need some addition as a one. Like that, there is a primitive things which we are discussing about. So in that there is emerges like CNN model is Python is not ready to deploy. So someone giving something whether the Python may not run on this or might run. A CNN model is a TensorFlow not ready for deployed in IoT Edge. The model we developed, it was in TensorFlow, but IoT Edge doesn't have a TensorFlow. In my home, I may not be having TensorFlow in my field. How I can deploy that your neural network on it. Then a trained CNN model might have a floating point weight. I might have run that one in Tirupati SITAMS college, very nice computer, everything like a 64-bit floating point. When I take it in the Tanjavur Agri Farm paddy field, I will not have that kind of computer even to have 64-bit computing, right? It might be 16-bit computing on the tractor. How would I use that one? No way, right? Trained CNN model might have too many neurons. So when you see SITAMS labs, then you have a huge, lab infrastructures. You have a terabytes of memory. You have a neural network model, 4 million neuron or 10 million neurons. Can we carry the 10 million neurons to the field deployment tractors or like kind of camera in the on the field where such kind of massive neurons also can be deployed on that. That's that also another. Then IoT Edge technology is very different from deep learning based inference technology. Is it true that IoT is totally new or something which is what we inherited from the world? All the above are true. Is it that everything is true? I leave it to you. Think on it. So it might open up some of the thought process on your mind. With this, basically, I architect these questions not to check whether you understood or not or something. I look at this place like a gateway for you to open thinking. That's the way I just put into that. So, of course, you are all good in writing a questions and evaluating students. So you are all being a teaching profession. That's bread and butter for you. But I'm not in that profession. So in R&D things and software engineers, I wanted them to think much better than me, such that things goes well. The questions are architects that we actually have open up things, reading the directions and understand more, and bring value, enrich the knowledge on that side, and be more fruitful to the society. Of course, we are with assuming that we are done most of brainstorming and images and how the computing on the images, object detections, and how to track the problem from one end to another, and then what kind of complexities, then what kind of history was there. We added bit of history also, Alex and so case for history also hinted, and also we added bit of problem areas where it will come like agriculture, our homes in villages, and transport our roads in villages, and of course, our hospitals, people in a life-saving effort to rescue, people. And of course, we have manufacturing places to making all the places in our hands without all these modern technologies, modern IoT, modern, deep learning things. So only bank people are only, I think they're only payment also. And otherwise they ask us to fill 20 odd pages of applications for everything. So there is no A, no green things are going on to that. But now the teaching, when you're teaching also, I'm sure most of you now gone into online teaching because of pandemic, most are bored and things. Imagine we want to teach the primary school, not primary school, pre-KG students by using AI. So I was quite fascinated that I took it very nicely. And when I was young, I was doing part of the project called One Laptop Per Child, MIT Media Lab project. When I was in US, I was fascinated that I was followed up. We did quite a bit of work on that. From then onwards, how to make learning is good for the poor people also. And how they can use the digital technology for them. That was basic thing. Of course, we innovated quite a bit on satellite radio. My dream was like Kalamsar is called tele-educations. My first company called Epicon Media Technologies. We are the only early people. Now even today, no one has done that. We World Space Satellite. We done the receivers, which is even a cost only 1,800 rupees actually. In those days, even set-top box was not that cheap. The set-top box used to be costly. So we have done that kind of receivers which can work in whether OT or like Assam or in a Kanyakumari or a Kashmir, because satellite doesn't require a terrestrial tower, right? It can work on that. So we have this kind of infrastructure for a school. And
excuse me, sir. Hello, sir.
Yes, please go ahead.
Session is another 5 minutes, sir. You can session will end up.
Yeah, almost we are done with the close one only. Another few slides on that.
Oh.
So now we have the application. This is a handwritten applications for LKG and the kind of people. How we are going to do that. So this is a complex process. I'll ask you to go through these things for separate one session working with IBM Watson. If you want to convert this problem into a solvable problem, instead of using our own process, if you want to use IBM Watson, you can use this complete a slides workflow. It's also this become IEEE course also part of blended learning programs, and same workflows increased more. These are the steps which is given, and notes also given on the particular pages. You can go and do it yourself actually. So that my evening I'm going to do only that side. No, IBM Watson I'm not going to do that. But since these slides are with you, you can do it yourself. Or in case if you need or somewhat help also will be helpful under. So I put it meticulously each and every step to do that. And also the source code also put it free for you web app. So you can mobile app. Well, web app code is this thing. Mobile app is very useful for you. I put that also. That you can download the source code and then get your credentials into that. You can have a nice application like this. You can get a wonderful applications, image classifications. Imagine like the input is like 0, 1, 2, 3, and the student when they write on the mobile phone, and then you can classify whether they written 3 or 4 or 7. So you can create your own application onto that. But the thing is that has to be linked with Watson's, IBM Watson, and the left side is your own application. We call it N-Farwise application. The whole source code is put it here. Complete source code is that you can pick it up. No charge, you don't need to pay any money. IBM Watson also free account, you can generate it. You can learn, it's very good. So a recap this is, we need this working. But what happens is, IBM Watson, one more questions also put here. We need a custom model for class. I was telling about Alex, he had his own model, correct? Like that, we have a custom model. How do you build that one from IBM Watson? That's a challenge, but the steps are given. All the steps are for that. You can look at that options. And the another one, deployment. After building the model, where we are going to deploy it, we are going to deploy it in the mobile phone, not in the Watson's. Or if you want to deploy it Watson, what will happen? What deployment phone, what happened? But today, this model deployment are happening on the Watson, not in the phone. So there are a few questions on that also. But I did not look at what you call deployment on the phone as of now. But the afternoon session, we look at the deployment on the phone, fully local. That is not connected into the servers. This is we handle it afternoon, but essentially the last 3 slides is going to recap for us, bring your own data set. Of course, data set is see text to now we have something called healthcare data, correct? It's going images, video, voice, audio, radar. Radar also become popular now actually, a millimeter. Industry 4.0 and healthcare. This data is also coming, red means too high, gray means too less in the volume of data. Of course, how to collect them, where to store them, how to read. There's a lot of challenges in the top side computing science challenges, but the domain experts in the bottom side as expert, bring this one. After that, we need to build our models. Of course, that's a challenge here. Everyone can build. There is no IEEE standard model as to like we have put 32-bit floating point IEEE format, like IEEE 32-bit. So, but so we don't have a neural network model standard for IEEE as of now. Maybe soon it might come up. Otherwise, we have to build our own model. Then after that, we need to train that model. That's the place we need a computing infrastructures, which I was telling you how done, which is done that way. Like you can compute that one CPU as well as CPU as well, and need not be like only one. Of course, still C++ you can do. CUDA also you can use it on that. This all you can do it in your own lab. We can have of course, Pawan has seen this. Dr. Pawan has seen this machine UVC when he was doing that. So that
yes, sir. Yes, sir. Yes.
This is a Power 9 machine, AC900 state of art machine. This is a part of many supercomputers around the world. So that machine you can have it in your lab. Also, it's not very expensive, not crores or rupees, maybe few lakhs of rupees. This is actual machine actually. This is sitting on my table backs in another room actually. So I use it in daily purposes. Of course, the GPUs also enter that. They're not very expensive. Labs can afford and put in. And after that, you deploy your own model on this here. These steps are given in it. Of course, data set is important. I use MNSD one. So you can, I'll take this question also 13. 14 is CNN model real train provides the following option create. So how do you create a custom model? So the question 14 will be interesting if you look at it, all the option with care. These are the steps for us to design a custom model. 15 is the training the CNN model by MNSD data. How the training going to happen on the top of that steps also elaborated in terms of 15. 16 is after training that one, how do you test it? That is put in a 16. 17 is trained data set model x86. Now the coming whether which machine you are going to train, x86 or GPU or CPI, how the interface or PCI or FPG, lot of complexity will come. 17 will be very interesting for you and want to build your own lab. You explore 17 with care. 18 is of course a deployment where we are going to deploy, whether going to deploy the trained model Android phone or Jetson Nano. This will be like applications specific one which comes like that. So that way, of course, it's a final one. It is a kind of a thing. This link I sent you, but maybe most of you can click that link. If I play this video, it's not coming here. Did you see any video now? No.
You can try. You can try in the afternoon, sir. This slide, if you would like to.
Afternoon. Okay. Okay. Good. The only 1 minute video. So already the link is given a chat session. You click on it.
Yes.
19 is deployment of training model by using a Docker image. So now things are happening, something called images. We built that also, platform independent, and if you build in your lab, if you want to give it your model in the PhD text some another lab, you can easily give a Docker image. They can easily able to run. They don't need to depend upon the installations and many other tools, hundreds of other tools. So it will be very nice. Most of our faculties in your lab, create this one kind of building Docker image for your applications, what you build it. So it's easy to share with others and easy to sell us, of course. Of course, I did give the references. If you have a time, please do look at that. The part 1, part 2, part 3. This is in the published in Dubai TechX Media. So this one write up, they split it into 3 because reading time, it's not should not be too high for them. They said, let us divide it into 3 parts. But it's a good reading one. If you are really keen on doing something on IoTs and then 5Gs and things and computing science world, if three things are well connected and what kind of data are the tools required, what is where presently people are driving towards, I very nicely written down. So you can read it with this. So most of my today presentations is part 1, part 2, part 3 when I gone through the whole thing. So I excited for that. For when I was asked for it, then I said, okay, instead of giving the part 1, part 2, 3, part 3, let me extract certain things and then talk to you all, and that's why today's presentation. Of course, the last slide is the most important, interesting one for all of us. Like how the today transistor works, how the futuristic transistor is going to work on it. Like as the source in the train and the charges are moving, what kind of channels, whether they follow Boltzmann limit, or they going to cross it, or still how far away from Boltzmann limit. That's what the thing. Of course, with this, I like to say thanks. Evening we'll discuss about the
Thank you, sir. Thank you for the morning session.
Yes.
I think participants can join at 2 o'clock session begins.
Yeah.
So about 10 minutes before that resource person will arrive. Excellent applications and concepts and all these things you are given in the demonstration in the morning itself, sir. I think we would like to know more about this thing in the afternoon session. So we welcome you for the morning session, sir. Thank you very much.
Thank you all. Wish you good lunch and have a nice day.
Yeah, we'll join back, sir.
Yeah, thanks.